So, then let us look at another example. So, the second example that I have today is the following. We want to look at the motion of a simple pendulum in the form of a holonomic in the form of a constraint problem with holonomic constraints. So, we want to see the motion of a simple pendulum of mass m and length L. Okay. So, let us just say that my vector q of t denotes the position vector. So, I am talking about a problem in 2D, right. I am talking about a problem in 2D. This is the position of pendulum, at time t, where I denote. So, this is the general notation. I denote q1 as my horizontal component and q2 as my vertical component, right, of this motion. Okay. So, further we assume that the motion is restricted in a given parameter range. So, the motion of the pendulum is for t from t0 to t1, right. And further, which means in our case our action integral, or which is the total energy integral, comes out to be an integral from t0 to t1 m by 2 of mod q bar dot square plus g times q2, okay, of dt. Note that this particular quantity is my kinetic energy of the system, and this particular quantity, which depends on the vertical component of the position, is the potential energy. Okay. Here we have absorbed. It does not really matter whether we have m here or not, the second scenario, because m is a constant of the problem. So, we can very well assume that mg or m or g as one of the constants. Okay. So, now we have a pendulum. Note that we have a pendulum which is rotating such that the total length of the pendulum is L. Okay. So, the pendulum, so that also brings in an additional constraints on the motion of the pendulum. So, the motion is subject to the constraint such that the sum of the square of the x component and the square of the y component, which is q2 minus L, right. So, q2 minus L. So, q2 is this quantity and q1 is this quantity here, the horizontal component. So, q1 square plus q2 minus L square, the total length must be equal to L square, right. So, this is my holonomic constraint. Okay. This is my holonomic constraint, and then further what I have is that so I am ready with my, so notice that I am ready with my functional. The functional is an integral with an integrand containing two variables subject to this constraint, which also is a constraint of for two variables, right. So, I can find the necessary condition for an extremal by solving my Euler-Lagrange equations, and I am going to directly write the set of two Euler-Lagrange equations for each of the components, which are as follows. So, q1 double dot plus 2 lambda t q1 is equal to 0, and the second equation is q2 double dot minus g plus 2 lambda t times q2 minus L is equal to 0, right. So, what I have is, we have set of two equations here, but three unknowns q1, q2 and lambda, but we also have the holonomic constraint, which is the box constraint here. So, I can solve, let me call this a system of equation as double star, because this box constraint is my constraint star. So, star and double star can in a sense be used to solve for three unknowns, which is q1, q2 and lambda. So, we end the discussion in this example by saying that these set of three equations are fully solvable for the set of three unknowns q1, q2 and lambda. So, then let us look at another example. Okay. So, let us look at another example, that is geodesics in 3D. So, we are revisiting the same class of problems with different setups. So, geodesics in 3D. Okay. So, now let us, so I am going to pose this problem of geodesics in 3D such that the point lies on the surface of the sphere. So, my equation of the sphere itself will serve as the holonomic constraint, right. So, let me call the constraint G to be G, and G be a smooth function. When I say smooth function, I necessarily impose all the derivatives exists, all the necessary derivative exists, such that my Euler-Lagrange equations are solvable. Okay. So, this is, so G be a smooth function of these three variables x, y, z, and further if we assume that we are not in the scenario of abnormal problems, then an equation of the form G of x, y, z equal to 0 describes the surface of sphere, of radius 1. Let me call this as my surface sigma. So, it describes the surface of sphere of radius 1. Let me call this as sigma. Okay. So, let us assume that gamma is the curve that we are after, or the extremal curve, and let me begin with by saying that gamma be any curve on the surface of the sphere. So, gamma is a curve, let me call this curve in 3D. So, what do I mean by a curve in 3D? We are saying a curve which lies on a three-dimensional surface. Okay. So, curve in 3D described by this function r bar of t, which is x of t, y of t, z of t, such that x, y, z follows the equation of the surface of the sphere. Okay. So, t is from t0 to t1, and the arc length gamma, the arc length of gamma is defined by this functional j of x, y, z to be the integral from t0 to t1 of the absolute value of gamma prime dt, absolute value, which is also equal to the integral from t0 to t1 of square root of x prime square plus y prime square plus z prime square dt. Okay. So, this is the functional that we have to optimize, that is the arc length functional. So, the geodesic on sigma is going to be the extremal of this arc length functional. So, geodesic on sigma is the curve with endpoints P0 which is gamma at T0 and P1. So, I call these points P0 and P1, which is gamma at these parameter values T0 and T1. Okay, so so I can directly go to the description of the extremal by starting to solve the Euler-Lagrange equation. In this case, my function for the Euler-Lagrange, so which means my f for my Euler-Lagrange equation, or the function that we need to be substituted for our Euler-Lagrange equation, is going to be, so if I call this as my L, and I call this, well, I have not written G. So G here is, G of x comma y comma z is nothing but x square plus y square plus z square minus 1, right. So, this is the constraint that is set equal to 0 if I have that the point x, y, z lies on the surface of the unit sphere, right. So, my f is L minus lambda of g of t, right, because x is a function of x, y, z is also a function of t. Okay, so which means my Euler-Lagrange equation are as follows. So, which means that d dt of partial qk dot, right, qk dot minus partial qk of f is also equal to the set of following equations. We break it down into the set of 3 equations, the first one with respect to x, the second with respect to y, the third with respect to z. So, d dt of x dot divided by, well, have I used dot or have I used prime? I have used prime. So, here my prime denotes the derivative with respect to t, right. So, let me continue using prime. So, x prime divided by square root of x prime square plus y prime square plus z prime square, okay, plus lambda of t times del g del y, this is equal to 0, times, and then the second quantity that we have is d dt of z prime divided by square root of x prime square plus y prime square plus z prime square plus lambda t of del g del, well, the first one is del g del x, del g del y, and similarly I can continue by writing the third, well, this is my second component. So, this is with respect to x, this is with respect to y component, and then the final one is with respect to z. Okay. Del g del z set equal to 0. So, this is my Euler-Lagrange for the z component. Now, we see that we have 3 unknowns x, y, z, and the fourth unknown is the lambda, and we have 3 equations plus the isoperimetric the holonomic constraint. So, technically we should be able to solve and find the solution x, y, z. However, we can see that the solution is extremely complicated. So, let me call this set, let me call this set as A. So, my set A can be written in a more general format. I see that my system of equations given by A, there are 3 equations in overall, is a second order ODE of the form u double prime x prime square plus y prime square plus z prime square minus u prime of x prime x double prime plus y prime y double prime plus z prime z double prime divided by x prime square plus y prime square plus z prime square. Okay, this is also equal to 2 lambda u, where my u is x, y, z. So, plugging in the values of u respectively will help me to generate each of these equations described by the set A, right. So, note that this is a second order differential equation. For each u, this is a second order differential equation, which means it has 2 linearly independent solutions, but however, there are 3 equations overall for u equal to x, for u equal to y, for u equal to z, right. So, what I said is the following. So, equation A holds for u equal to x, y, z. So, are there 6 linearly independent solutions? The answer is no. We have 4 variables. How can there be 6 linearly independent solutions, right? So, there cannot be 6 linearly independent solutions, right, which means that there will be a relation which relates at least 3 variables together, right, and then the other 3 variables are separate. So, at least there will be one relation. So, which means so if my 3 variables are x, y, z, so z can be expressed in the form of x and y. So, x, y, z are linearly dependent, right. So, given the fact that there cannot be 6 linearly independent, there will be at least one relation. So, there is at least one relation between 3 variables, so that the system is properly defined. So, let me call those 3 variables. Without loss of generality, the 3 variables could be x, y, z. So, which means that what I am saying is that ax plus by plus cz must be 0, or z is a function of x and y, c not 0, right. So, which means, well, so what is this relation? Notice that this relation is an equation of a plane. Okay. So far we are trying to solve our system of second order differential equation purely by reasoning and geometric arguments. We see that this equation, this linear dependence relation, is nothing but the equation of a plane which passes through origin, passing through 0, 0, 0, right, plus what we have is that x, y, z satisfies the holonomic constraint, or it lies on the surface, of sphere. It lies on the surface of sphere. So, which means that the points lie on the surface of sphere. The point also lies on a plane which passes through the origin, which means that the points x, y, z. So, the conclusion is that the points x, y, z lies on the intersection of the sphere and the plane passing through the origin. Okay. Or so x, y, z lie on the plane passing through origin and cutting the surface of the sphere, the surface of the sphere, right, and that is only possible if x, y, z lie on the great circle, which is exactly the result that we have looked at in the previous discussion of geodesics in 3D, right. So, this is another approach of solving this problem by using a holonomic constraint. Okay. So, I end my discussion on holonomic constraint and then move on to our discussion of non-holonomic constraint optimization. We will see that non-holonomic constraint optimization is a more general situation. So, non-holonomic constraint, right, or we call this class of problem as the Lagrange problems, okay, or the Lagrange problems. And let me just write down the basic statement of this constraint optimization. So, we want to determine the extrema, of the functional j of q bar, which is integral from t0 to t1 L of t comma q bar dot dt. We call this relation as A1, subject to the boundary condition j q bar of t naught is q bar naught and q bar of t1 is q bar 1. Let me call this condition as A2, and further and the constraint of the form g of t comma q bar dot is equal to 0, right. Let me call this constraint as, denote this by A3. Okay. Now, I am going to show that this class of constraint problems is a very general class. In fact, the class of isoperimetric problem is a subset of this class. The class of problems where we look at the generalized case of Euler-Lagrange equations with functions having higher order derivative is also a function of this class, is also a subset of this class, and so on and so forth. So, this class is quite general. So, what I am going to show is that in fact, our class of isoperimetric problems could also be posed as a class of non-holonomic problems. So, isoperimetric problems are a subset of Lagrange problems. Okay. And how? So, which means that my integral constraint can be posed as a differential constraint. So, to show that, let me consider the integral constraint in isoperimetric problem. So, consider the constraint of the form IQ, which is integral from t0 to t1 of g of t comma q bar dot dt. Okay. This is equal to L, right, where my q bar is a vector of the form q1, q2, qn, and to pose this integral constraint as a differential constraint, we introduce a new variable. We introduce a new variable qn plus 1 by the relation qn plus 1 is equal to the integrand of the constraint g of t comma q bar dot. This is also equal to 0, right. So, introduce a new variable qn plus 1 by the constraint qn plus 1 dot is equal to 0, right. How does this help our situation? Which means that, notice that if we integrate this quantity, then integral of q bar integral of qn plus 1 dot will be qn plus 1 from t0 t1 to t0, which will be, so integral of this left hand side will be, so let me finish the statement and then it is quite easy to see. So along with the boundary condition, that qn plus 1 t naught qn plus 1 t1 such that the boundary condition is qn plus 1 t1 minus qn plus 1 t naught is equal to L. So this is my boundary condition satisfied by the new variable. And how does this help our cause? Notice that we now, if we integrate this boxed relation, well, let me call this is the relation that we have. So if we integrate this boxed relation, we see that the left hand side of the integral will be qn plus 1 at t1 minus qn plus 1 at t0, and that is equal to L from the boundary condition that we have posed, and the right hand side is the integral given by the isoperimetric constraint. So now instead of using this constraint, if we use this particular constraint, then the problem is identical. But so the first constraint is an integral constraint and the second constraint is a differential constraint. So the isoperimetric problems are a subset of Lagrange problems. So we could have, so the Lagrange problem discusses all classes of isoperimetric problems as well. Next, let us also look at the problems involving higher order derivatives. So problems involving two or higher order derivatives, derivatives in the integrand. Okay. So we are talking about the functionals of the following form: g of y is equal to integral from x0 to x1 of f of x comma y prime y double prime d of x, right. So how about this class of problems? Notice that if we introduce new sets of variable, so we are going to introduce variables of the form, new variables t is equal to x, we introduce q1 is equal to y, we introduce q2 is equal to y prime, right. So here it means that q1 prime is equal to q2, right, q1 prime is equal to q2. So then, so this is a condition which is our non-holonomic constraint. Okay. So this is our non-holonomic constraint, and now notice how my functional reduces to. My functional j of y now is j of q bar, which is now integral from t0 to t1 of f of t comma y was t comma q1 comma q2, and the last variable y double prime is nothing but q2 prime. Okay. So now we have reduced our function, which is the integrand of this functional, originally dependent on functions up to second derivative, to now dependent on functions up to first derivative with the additional non-holonomic constraints, right. So now we can see that the higher order derivative problems are also, these two are equivalent, are also a subclass of Lagrange problems. Okay.